Well, once we are able to find the state of stress at any given point in a piece of material, that actually doesn't take us the whole way of the whole question that we need to answer, all right? Generally, the reason that we would want to know the stress that is being carried in an element of material is we want to know how close is that piece of material to breaking, right? That's ultimately the reason that we would even care in most cases why, or care what the stress was at a particular point in a material. It's to answer the question, is it close to breaking at that point, right? So that's the direction that we're going with this, but there's a key piece of theory that we need to touch along the way, and that is stress transformations is the kind of a big heading that I could put on the whole theory. And the reason that stress transformations are important is a state of stress sort of is what it is, but it will have numbers that are associated with that state of stress that vary depending on the coordinate system that you use, right? So if you define a little element of material so that it's aligned according to one coordinate system, and that piece of material has a state of stress in it, that state of stress is the same as if you had a different set of coordinates, even though the actual stress components that you would identify change. The stress components are part of a bigger picture, and that is the overall stress state, right? So even though the actual, like the X, Y, and Z normal components, each of them could change if we rotated our coordinate system that described the piece of material, right? Even though all three of those could change, as could all of the shearing stresses that occur on the body, the state of stress isn't different. Does that make sense? Like the state of stress kind of is what it is, which is a good thing because that ultimately is going to control whether or not the material will fail, right? The state of stress along with data about the strength of the material can be used together to figure out whether or not the material will fail, okay? So toward that end, we are going to do a little bit of theory today talking about a technique called Mohr's circle. So Mohr's circle is a method of taking a given state of stress and turning it into some other parameters that might be helpful for us to really have a good idea as to what this actual state of stress is, right? And some of those parameters are called principal stresses. So that's one of the big things that comes out of a Mohr circle analysis is you figure out some principal stresses, all right? And we'll just define what those are as we move along. To start this whole discussion, I actually show two different figures here. The left figure is a full state of stress that a little three-dimensional element of material might experience if it was anywhere inside of a body. So in other words, imagine that you might have a shaft that was twisting, right? And one of the things that you very quickly did in your mechanics of materials class is you saw that the worst case state of stress for a shaft that was twisting was out on the outer surface, right? You remember that? Like the further away you go from the center of twisting, the more stress it was carrying. And so the worst case scenario was out on the outer surface. Well, it turns out that that's the way it is for most types of stress. Usually your worst case is going to happen out on the outer surface of your parts that are being stressed, okay? Now, having said that, that makes those particular elements easy because you have what's called a free surface. So if you're twisting a shaft like this, all of the material that's on the outer surface of the shaft, you can look at it and see that on that outer surface, there are no applied forces, right? So what we call that is a free surface, right? It doesn't have anything touching it, right? It has nothing touching the outer surface of this shaft that's being twisted or a beam that's being flexed. Typically, if a piece of material is on the outer surface of a part, it very frequently is a free surface. And once you see that something has a free surface, you know that the state of stress reduces from this general case where it can have three components of normal stress and three components of shearing stress. It reduces from that down to a state where you can have two components of normal stress and just one component of shearing stress. All right? Essentially, most parts the worst case state of stress occurs at a location where there is a free surface. And so in this particular example, this would be the free surface, right? And because that's a free surface, there's no stresses applied to that surface. And so that basically eliminates, sigma z, tau zy, and tau zx from our state of stress that would be the more complete three-dimensional state of stress. Okay, we good so far? So I'm trying to get you this idea that, for any element of material inside of a body at any location, you need these 6 components of stress to fully describe what the stress is at that point. Once you move to the outer surface of a part, as long as the surface is a free surface, it means that you can reduce it down to a state of plane stress. All right? And I may have kind of beaten that to death, but that's where we're going with this. And the state of plane stress is where Mohr's circle is very useful. Our next lecture that we do, we're going to talk about how to deal with it if you have a full state of stress for an entire cube. And how do you figure out things like principal stresses in that case? All right, but today we're going to focus on the case of plane stress, which is a very valuable case because this is where the worst case state of stress often occurs, is on the outer surface of a part where it has plane stress as the state of stress. All right? All right, so that's kind of where we're going with this. So let's look at the cube that I defined up there, such that it is carrying this plane stress. Okay, so you see there it has sigma y going in the y direction, sigma x going in the x direction. Those would both be normal components of stress, as well as this component of shearing stress, tau xy. Okay, and for some of these, I've actually labeled them as tau xy, and then another one is tau yz. There are some texts where they actually split that up, and they might talk about those as 2 different values. We're not going to do that. So we're going to just assume that any shearing stress I have on, say, the surface of the cube where the x-axis points out, I'm going to assume that shearing stress is going to be the same as the shearing stress on the side of the cube where the y-axis points out. Okay? So what we're going to do here is we're going to imagine that for this little tiny element of material, imagine that we're going to take a cut through that element of material such that the cut is rotated inside of that piece of material. So that cut that I'm talking about happens right here. Okay? And I'm going to look at how the stresses that are being applied here, sigma x, sigma y, and tau xy, I'm going to look at how those stresses would have to transform so that we could figure out what kind of stresses those stresses would apply to the surface that I now created by making this planar cut through the middle of the element. This is what allows us to transform the state of stress into a new coordinate system. All right, the ability to rotate like this. And for a state of plane stress like this, really the only rotation that we're concerned about is a rotation around the z-axis. So that we get that by having this plane that we're now cutting through right here. Well, if I look at that kind of straight down the z-axis, then you see the picture that I'm showing on the right. Right? So you actually have this plane that is now cut through the middle of this element. Right? And what we want to do is now figure out what kind of stresses are implied that will be applied to that surface, given that we had our sigma x, sigma y, the 2 normal stresses there, and the tau xy. So what I'm going to do is look at that little element of material and sort of extract it out of this element. Okay, that's what we have shown right here. I'm showing here a normal stress that is applied on that surface, and I'm labeling it sigma n. And then I'm showing a shearing stress that I'm labeling tau sub nt. All right, and the reason I'm labeling it that is I've essentially established a normal tangential coordinate system relative to where this cut was made. Okay, so far so good? All right, and further, we have this angle that describes how far have we rotated this coordinate system. Okay, that angle phi. All right, so that is what we're going to work with, but what we're going to do is we're going to take that and now orient it such that my normal and tangential coordinates are aligned, normally relative to my page, and that helps me see where these other stresses applied would act. And this is where all the business gets done, right here on this figure. Okay, this is where all the business gets done of doing the transformation into this new coordinate system. All right, so we're talking about stresses, and in order for us to use a free body diagram method, can we do that in terms of stress? Okay, free body diagrams, typically we converse in what kind of a unit on free body diagrams? Forces, right? So we need to transform what were stresses on this free body diagram into forces instead of stresses. Well, how do you go to force from stress? You have to multiply by area, okay? So what I'm going to do here is a couple of things. First of all, I'm going to acknowledge that this thing is infinitesimally small, okay? It's extremely, extremely small. And I'm going to do that by calling the amount of area where this, where this element was cut, and it's hard to see it there, but I kind of made a little projection back like this. Imagine that this little element sticks into and out of the page a little bit, and I'm talking about that little amount of area right there, and I'm calling it dA. Okay, so I'm kind of acknowledging that this thing is really small. That's why I'm saying dA. But that dA that I have actually relates to the amount of area where my other stresses are applied. For instance, over here where my sigma x was applied, right? This guy right over here was sigma x. Okay, it has an area that it's applied to as well, and the area it's applied to is related to the amount of area that I had up on the upper surface. Would you agree with that? So if this thing all has a uniform thickness to it, then how those two values relate to each other, they're basically proportional as the length of the sides are proportional. Do you agree with that? So since they're all the same depth, then the amount of area I have is basically, imagine the proportionality of this side over here to this side over here. Okay? That proportionality would also hold for area because it has a uniform thickness. Okay? And because of that, I can basically take the amount of area that I had up on the upper side and multiply it by the cosine of phi, which gives me, that would, if I was doing length, that would give me the length of that side. But since I'm using area, it actually gives me the area of that side because it's all the same thickness. See how that works? So I've kind of discussed that now for sigma x, and I'm saying sigma x now times the cosine of phi times dA. That gives me how much force would be applied on that face. All right, following? All right, I can do that for shearing stress as well, right? It's the same amount of area that this shearing stress tau xy is applied to, and so I would also multiply that by cosine of phi times dA. We good so far? Okay. Over on the other side, that side now relates according to the sine of phi, right? Because we have this right triangle, opposite over hypotenuse, right, is your sine function, right? So I'm using the sine function for, these relationships down here. Okay. And by using the sine function, I'm applying the amount of area that those stresses are applied to. All right. So that's good. And so now we actually, by multiplying in this way, we have actual force values that are being applied. But they're not all applied in the same direction, are they? So now we have to do a sum of forces, one sum of forces in the normal direction, right, according to this normal component that I showed up here, and according to the tangential direction, which is shown over here. So that's our next thing, is to write equilibrium equations for this little infinitesimally small piece of material. Okay? And here's what that would look like. Okay? And to help you understand what we're doing here, I color-coded where each of the terms came from. Okay? So I've got the original stress that's in red. It gets multiplied by the cosine of phi times dA. That much turns it into a force rather than a stress. Okay? And then I have to multiply by another trig function to pick off the component that acts in the normal direction. Okay? So let's look at that very first, this very first term right here. Okay? What I'm doing is I'm picking off the component of the, the force over here that I colored green. I'm picking off the component of that is aligned with the normal direction. Okay, so I had to multiply by area to get force, and then I had to multiply by another trig function to pick off just the component that is pointed along the normal direction. And you might notice that I have a negative sign out there. Why do I have a negative sign? Right, the direction that this arrow is pointing is opposite the positive direction that I had established for my normal direction. Okay? Well, that's basically what happens for each of the faces. Right? I've got a lot of stress components, but each one of them has the original stress component multiplied by a certain amount of area to get a force, and then multiplied by another trig function to pick off the component of that force that points in the direction I'm interested in. All right? And I do that for all of my normal components, right? Or all of my components, the normal component of each of them, okay, according to the normal direction that I've established. And then I do that also for the tangential direction. Okay? About the only other thing I maybe should mention is, what about the sigma n that I established right there at the beginning? Okay? That just gets multiplied by dA because that was the area I had originally set up as being that area of that top piece. Okay? And so, and same with tau sub nt. Okay, so I think the question is is sigma n kind of, can you think of it as an equal and opposite reaction to the stresses that are being applied? And I think that's a reasonable way to think about it, right? You've got sigma x, tau sub xy, and sigma y that are all being applied to this. Well, the combination of all of those had better be reacted with sigma n, right, in order for this to stay in equilibrium. Okay, and the same could be said for the, that tangential component right there. The same thing can be said there, that you have to have some amount of shearing stress there to keep it from accelerating left and right. All right, well, this is the starting point, right? This is, now we have relationships that allow us to relate sigma x, sigma y, tau xy, sigma n, and tau nt. All right, we have two relationships basically there. Well, since everything has dA in it, we can now divide it out, right? We can divide it out of the whole expression. And what that leaves me with are some expressions, two expressions that look like this. All right? And with expressions like this, we can go a little bit further and factor out a cosine phi sine phi that you see right here, or basically 2 times cosine phi sine phi, right? We can factor that out of the first expression. And we can also factor out a sine phi cosine phi out of that first couple of terms in the tangential direction. With me so far? Okay. So then the next thing that we do is we go back and rack our brain about certain trig identities that we have almost all assuredly forgotten. All right. Hopefully not, but I'll say that these are not things that I necessarily keep on the tip of my brain either. All right. So we can go back and remember that we have some trig identities that we can use, and a few of these are called double angle formulas. And what we're going to see here in a minute is they are going to be interesting because they're going to lead to some factors of 2 in our final expression that you may not have predicted, and they largely come out of these double and half angle trig identities. All right, so what we're going to do is take these trig identities and plug them in. Okay? And once we do that, we wind up with two expressions that look like this. Okay? So we're basically plugging in something for cosine squared of phi. We're plugging something else in for sine squared of phi. There's another place where we have a product of sine phi, cosine phi. We're essentially doing substitutions for each of those. And we're creating these two expressions here. All right? And these are extremely important. The reason that these are important is these are the functions from which we get Mohr's circle. Okay? One of the things that I studied when I was in an algebra class was the idea of parametric equations. If you wanted to be able to plot functions, you could do it with parametric equations. Do you remember seeing anything like that when you were in algebra? Okay? And the concept there was that you would establish a parameter that would be common between two different equations, and one of the equations would plot an x value, and the other equation would plot a y value, and you could vary the parameter, and it would cause both x and y to vary, and you would just plot those x and y coordinates for each value of the parameter that you established. You remember doing something like that when you were in algebra? All right, well, look at this expression from, through that lens. Okay? What if we're going to plot normal stress, sigma n, and shearing stress, tau sub nt, and we're going to do that where phi, which is the angle that we're going to have rotated our coordinate system through, is the parameter. All right? So it allows us to find any rotation that we want for our coordinate system and be able to know what the normal and shearing stresses are on a plane that cuts through it for any angle that we cut through, and we can sort of plot all the possibilities, right? Where that, that angle that we choose is the parameter, and we're going to plot on a set of axes both the normal component and the shearing component on the same set of axes. Okay? Well, here's what that would look like. Okay, so I took those functions that we just created, right? We went through from the very beginning and figured out what these stress transformations were. And now what we're plotting is shearing stress and normal stress. Shearing stress on the vertical axis, normal stress on the horizontal axis. And we're going to let phi vary through all the possibilities. And what do we see? It makes a circle. Okay? This is where Mohr's circle comes from. All right? And this basically establishes that, it makes this entire circle. Now, one thing that's interesting here is, I'm moving this from negative 90 up to 90 degrees. How is it that this makes a circle if I'm going from negative 90 to 90? Okay? I heard some people say 2, right? What do I have 2 of? Okay? For each state of stress, there's actually 2 points on the circle. Right? And we move through essentially 180 degrees, and that traces out a full circle. Okay? Now let me actually pick off a few things about this circle that may not have looked obvious from the very beginning. So the first thing, these circles are always centered at 0 shearing stress. Okay, so the circle can't go up and down off of 0 for shearing stress. The middle of the circle, the center of the circle, is always aligned on 0 shearing stress. If you go back and look at the equations, could you have predicted that? Okay, maybe, maybe not. There's certainly something in the shearing side of the question, or something missing in the shearing side of the question relative to the normal side of the question, right? Look at this term right here. Okay? That term right there says that there's going to be a shift for the normal piece, right? And that is just going to be a pure function of the two values that we have of normal stress and not a function of phi or theta, right? The rotation angle for our little element of material. That is why this point is shifted horizontally along the axis here, but there isn't such a thing that exists on the shearing direction, right? So it's always going to be on 0, okay? All right. Where does the maximum shearing stress occur? Up here or down here, right? Which is actually the same state of stress. All right? So that's kind of interesting. And what else? What else is interesting that comes out of this figure? To me, the most interesting thing that comes out of this figure is the existence of another state of stress where there is 0 shearing stress, right? And this will always exist for a state of plane stress. There will be a direction that you can choose such that you eliminate shearing stresses, all right? Those values that I just identified right there, those are called principal stresses, all right? So let's move on just a little bit more. Once we get these expressions up here, one of the things we can do is take a derivative and set it equal to 0. Why is that? Why might that be helpful? Okay. One of the things that you can do out of calculus is you can find extremes. You can find the maximum that something becomes or the minimum that something becomes basically by taking a derivative which finds a slope at any point, and you set that equal to 0, and that finds where you got to maximums, right? Either maximums or minimums, right? So I'm doing that here and taking the formula that I had for normal stress, differentiating with respect to phi, and setting it equal to 0. Once we do that, it allows us to find a particular angle where normal stress extremes are. All right? I can then take that angle and plug it back into the original function, and what does that give me? Okay, it'll give me a particular phi once I set this up. What if I take that phi sub p that I'm calling it there and plug it back into my normal stress equation? That should give me my principal stresses, right? Because principal stresses, one of the things you notice here is that along the normal direction, you reach some maximum and some maximum, right? That's what I'm finding by using this technique. It's kind of the maximum and minimum that happens there. Okay? We can kind of do the same thing with respect to shearing stress. What are we finding there? Essentially what you're finding is the angle that you would need to rotate through so that you could figure out this maximum up here for shearing stress, or the maximum down here, minimum. Okay? At the end of the day, here's what you need to know. Okay? Your maximum normal stress, okay, or the normal stress at maximum shear is going to be equal to that value identified just a second ago, right? It's going to be equal to that shift amount that we went from 0 to where this center exists. Okay? And if we want to know what the principal stresses are, which I'm naming sigma 1 and sigma 2, by plugging those values in, you can end up with a expression like this, plugging the values in for phi. Okay? This is where all of our theory for Mohr's circle comes from. We ready to work one? All right, let's do it. So we have an element of material that is experiencing plane stress, okay? And I have it set up in ZX coordinates. All right? Does that matter? Okay, it kind of matters. Doesn't matter that much, but it matters a little bit. Okay? The reason it matters that I have this set up is I need to know whether or not I have my coordinate system set up in sort of a standard configuration. You remember the the little rule of thumb that I gave you last time to know what your standard configuration was going to be? Okay, I'll do it real quick one more time. You had a little element of material. In XY, it's easy. You're used to always seeing XY like this. Okay, and when you have it something in that situation, shearing stresses are positive this direction. Okay. What about YZ? Okay, kind of the same. We just shift Y over here and we put Z up there, and we say this would be our positive shearing direction according to the sign convention for that set of coordinates. Okay, what was the one I said people were going to probably mess up if they messed anything up? Okay, XZ. And so it's important for you to understand that to set up a set of XZ coordinates such that they're in kind of standard orientation, you need to put the Z in the horizontal direction and the X in the vertical direction. And then when you see stresses that are being applied like this, shearing stresses, that would be counted as a positive shear. Okay. The other thing that you had was something on your quiz today, right? You had a question on your quiz today that asked what? Okay, so when you have a shearing stress, what direction would that shearing stress make the thing rotate if it was in a positive direction? And the answer was what? Clockwise. And that probably feels a little bit counterintuitive to you because you're used to everything being positive counterclockwise. I'm not quite ready to do it, but I am going to show you why that's the case as we solve this problem. Okay? All right, so what's our first step? Okay, let me show you this. We'll kind of take apart what this formula right here is really saying. Okay? First of all, I can figure out where the center of Mohr's circle is going to be by doing what? Okay? I can calculate basically the average of my normal stresses. Right? So let's just do that real quick. What's the average of my normal stresses? Okay? Make sure that you account for your signs correctly, right? So we would want to do 25 is positive because it's a tensile stress. And what about 10? Okay, it's compressive, so I make that negative. Okay? So at 7.5, that is where the center of Mohr's circle is going to be. Okay? So, tell you what, I'm actually going to try to draw this more or less to scale. Okay, so 1, 2, 3, 4, 5, 6, 7.5. There's where the center of Mohr's circle is going to be. All right, now what's this other term? It's a square root of a sum of squares, okay, where one of them has to do with half of the difference between my normal stresses, okay? half of the difference between my normal stresses. That's interesting, okay? And the other one is the shearing stress that's being applied in this XY orientation, okay? Yeah, that actually represents a radius of this circle. Okay, that second term over there actually represents a radius of Mohr's circle. One of the things that makes this actually maybe easier for us to evaluate is instead of even looking at this expression, let's understand that the values that I'm given here represent one state of stress, and that one state of stress can be represented by 2 points that exist on Mohr's circle, right? I don't need to do the whole circle just yet. Why don't I just plot the 2 points, right? One of the points has to do with the face up here and down here, okay? So let's plot that point that would exist on Mohr's circle, okay? So I would have negative 10 KSI along the normal direction, okay? So 1, 2, 3, 4, 5, 6. Tell you what, I might need to change this just a little bit. I'm going to go half scale. Okay. So this was going to be 7.5. Okay. So 1, 2, 3, 4, 5, 6, 7.5 would be right here. Okay. And I want to go to negative 10 KSI. Okay. So I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right here. Okay? And at that 10 KSI, how much shear do I have? Okay? So I'm going to kind of do a vertical line like this. Okay? I have positive, someone says, 9 KSI. Okay, so since it's clockwise, we're going to go to 9, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and I tell you what, I'm going to make that a little red dot right there. So that is the location in this Mohr circle plane for the stress that acts on the upper and lower faces of this little rectangle. Okay? Now what about the stress that acts on these side faces? Okay, I have 25 KSI there, right? So let me just count that out here. I've got 1, 2, let's see, I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 25. Okay, and how much shear stress do I have on that face? Okay, also 9 KSI, but is it positive or negative? Okay, that one tends to rotate this thing counterclockwise, which I count that as negative, okay, over here. So I basically take this, let's see, 2, 4, 6, 8, 10, so it'd be 9 right there. Okay, so a lot of times once you establish that your state of stress that you are actually looking at, you know, in the orientation that you are given, a lot of times you establish that as being sort of this line. And you'll notice here that that line is going to pass directly through the center that we established by looking at the equation just a second ago. All right. The other thing that you might notice is that this value right here, I'm going to show a little rectangle, or excuse me, a triangle right here. That height right there is tau xy. right? What's this length over here? Okay, that's going to be half the difference between sigma x and sigma y, which this was over here, sigma y. This over here was sigma x, right? So half the difference between sigma x and sigma y would be the length of that side right over there. Okay? And therefore, this radical that I'm showing up here would be the length of the hypotenuse. Well, that makes sense because essentially what you can do is you can say, well, that's the radius of Mohr's circle. And once you know the radius of Mohr's circle, then graphically, you deal with that by saying, well, I could extend this circle around to the point where I found where it intersected here, or the point where I found where it intersected here. Right? And those would be the principal stresses. And actually, you know, I'm going to use a little bit different notation here. I'm going to call this sigma 3. Okay? Why do you think I'm calling that sigma 3? Well, here's the thing. Every element of material is going to always have 3 principal stresses, even if it's in a state of plane stress. Okay? Because we live in a 3-dimensional world. It just so happens, though, with a state of plane stress, you know, all of our transformations can happen around an axis that's aligned with the direction where we have no stress, right? And the stresses that we would have had in that direction will be 0. So what's our other principal stress? Okay, I found one of my principal stresses graphically over here, sigma 1. I called my other one over here sigma 3, but there's another one. Where is it going to be? Okay, it'll be out of this plane. That's true. Okay, think about what this, if this was a cube, right? Okay. So this is a cube like this. Okay, and I have, what direction do you want to set up here for my different directions? Okay, I'll tell you what. We said a second ago, I'll try to make it aligned as well as I can with the picture I already have. Let's say that this is my z direction. And this is my x direction. Okay, what direction is y? Okay, and if this is in a state of plane stress, then where are these stresses that I just identified on this square? Okay, one of them, you know, the shearing stress would be up here, right? Like this. That shearing stress value would be 9 KSI. And then I would have a compressive stress here, right, of 10 KSI. And then I have this tensile stress here of 25 KSI. Okay, so now look at, say, the comparison between x and y. Okay, what if I was to draw this picture such that I was oriented along my x and y? What would I have? The only thing I would see would be what? Just the 10 KSI compressive stress, right? The other ones would be out of plane. What if I looked at my YZ plane? You would see the, okay, 25 KSI tensile stress, but the other ones would be out of plane, right? And so what I'm trying to drive at here is our other component or our other principal stress that's going to be involved with this is going to be 0 because we have this free surface that I didn't have to deal with. Okay? So if I wanted to plot another principal stress, I could show the other principal stress right here at 0. And that would take care of my third principal stress. And one of the reasons I'm numbering them like this is I'm going to go ahead and get you used to, right now, I'm going to get you used to using some common notation that is used whenever we're dealing with principal stresses. Usually what is done is you order them such that the one that is the most positive, right? That doesn't actually mean it will be positive. It's the one that's furthest along the positive number line. Okay? You number that one sigma 1, right? The one that's furthest negative, right? The furthest to the left on the number line, you generally number that one sigma 3. And then the one that's in between the two is generally numbered sigma 2. There's nothing magical about that other than that's just one of the standards that people use to report principal stresses. All right, shall we finish our problem here? So how do I find principal stress? Okay, sigma 1 and 3 is just going to be equal to 25 KSI minus 10 KSI over 2 plus or minus the square root of 25 KSI minus a minus 10 KSI over 2, all of that squared, plus 9 KSI squared. Okay, so go ahead and plug these in here. 25 minus 10 over 2 plus square root of 25 plus 10 over 2 squared plus 9 squared. Okay, so I end up at 27.179 KSI. And what about my other one? Okay, same idea, but subtract. So negative 12.179. So those are my principal stresses that exist at those two locations. Well, what if I want to deal with my maximum shearing stress? I'm not sure if I'm drawing this nicely or not. It doesn't look like it's going to win any art prizes. But where we get up to up here and down here is what we're talking about. Well, how do I know that? It's just the radius of the circle. Okay. And so the radius of the circle is just the square root of 25 KSI minus a minus 10 KSI over 2 squared plus 9 KSI squared. Okay, and so all I would really have to do over here is just delete some stuff. So 19.69 or so. KSI. All right. Good enough so far? Any questions that anyone wants to ask or have answered? All right, the next thing I'm going to do here is probably for most folks the most confusing part, and it has to do with finding the angle where the principal stresses occur. Okay, this is also going to give me fertile ground to talk about why it is that the stress orientations that we said a second ago, such that one, that acts in a kind of in a rotational clockwise direction, why that is counted as positive. Okay, so first of all, let's just do it. How does the angle on Mohr's circle relate to the angle on the actual element? Okay. It's twice, okay? So how do you know that? Okay. This equation that we have over here has a factor of 2 in that tangent function. Okay? And that came from our, kind of our double angle formulas, if you want to trace it back. There's this factor of 2 that winds up in here. What does that mean in terms of physical interpretation? Here's one way you can look at it. I found this point over here. That point was describing what face where stress was applied. Yeah, this one right here. So we were talking about the top and bottom faces of this square. Okay? When I did this one over here, what face was I dealing with? The sides. So let me ask you, physically, how much angle is there between the top face and the side face? 90 degrees. And how much spacing do I have angularly on my Mohr circle between those two locations? 180 degrees. So we're saying a 90-degree spatial difference in the real world leads to a 180-degree spacing difference on Mohr circle. All right? So that's one way of viewing it, right? When you're looking at these 2 points, you're actually looking at things that are only 90 degrees apart from each other in actual space. Okay? All right, and so we're basically saying that the state of stress we actually have, which is described by this line where we have these 2 points, if I want to go to the point where I've got my principal stresses, I have to rotate this by some little angle. And that little angle, I called it up there phi sub p. Okay? How do I find that? Actually, I called this what? Not phi sub p. 2 phi sub p. Okay? So how do I find 2 phi sub p? Geometrically, like using geometry. Yeah? How do you know which direction to draw the angle? Okay. So what you're kind of doing is you understand this one over here came from my 25 KSI normal stress. Okay? And what I'm trying to do is go from there to another location where I have my principal stress. Okay? So let me actually do it this way. It's a really good question. There's this element of material. If you look and see what happens as far as strain to this piece of material because of the shearing stress, what happens according to strain? Okay, that little piece of material probably, instead of being square anymore, it starts to become a shape more like this. Do you agree? So what happened linearly along that direction? Did it get longer or shorter? Okay, it got longer. So it makes sense to me that if we had no shearing stress, right? Where we would have our normal, our maximum tensile normal stress if we had no shearing stress would be along this 25 KSI axis. But in order to figure out where we really have the maximum normal stress effect, positive, right, it's going to add a little bit because that shearing effect essentially is stretching this body along this direction. So what we're saying is I had better rotate a set of axes up a little bit like this in order to capture where that maximum normal stress effect occurs. Okay? Now, that corresponds perfectly with what I'm doing over here. I have to rotate this counterclockwise, right? I have to rotate from the state of stress I'm given. I have to rotate counterclockwise to get to the state of stress where I have my principal stresses. Just like here, I would have to rotate these axes, you know, to a new location here. Oh, and this was x. That one actually would be x prime, but this one over here would be z prime. There we go. Okay. So this, I mean, the idea of it makes sense, right? What I'm given, the orientation that I'm given is not the orientation where we find our principal stress. I have to rotate counterclockwise a little bit to find that location where I have my principal stress, just like I'd have to do on my Mohr circle diagram. I have to rotate counterclockwise a little bit to find my principal location. All right, so based on the geometry of the circle now, I can say that the tangent of 2 times phi sub p is going to be equal what? Tau xy over what? Okay. Okay, so I go ahead and plug these values in, right? 9 KSI. And then down here, I had 25 KSI minus a minus 10 KSI. Then that was all divided by 2. So if I take the inverse tangent of that, it gives me 2 times phi sub p. Okay, so there I've got 9 over 25 plus 10 over 2. Okay. And what if I just want phi sub p? Got to divide that by 2, right? Okay. Now I've got my calculator in radian mode. That was not on purpose. I just had it left over from before. Put it in degree mode here. And that gives me 13.61 degrees. Okay. Which means, what is my actual angle on this figure over here? Like this actual angle right here would be what? Yeah. 27.22 or so. Okay, so let me actually just tie a bow on this by saying this. A lot of people get confused and they're uncomfortable with Mohr's circle. And I think the reason that most people are uncomfortable with Mohr's circle is they want it to mean something physically. Okay? And that's not really its primary purpose. I mean, it has relationships, right? The relationships that we found on here do have relationships to the real world. But Mohr's circle is not an actual, like, spatial entity. Okay? It is a solution tool. It's a way to help you understand these expressions that we derived. And it's a way to quickly visualize a state of stress, all right? But the circle itself is not something that exists really in space. It's more of a solution tool, right, that helps you find things like principal stresses, right? And if you're not trying too hard to make it mean something spatially, then you might do a little bit better, right? It's more of a visualization tool for using the items that we derived earlier in this lecture. Okay? So I'll actually say this one more time because I think this is a really good point that I hope everyone caught, right? If you look at shearing stresses, it's pretty easy to look at them and tell what direction they are likely to elongate the member, right? Just by this little visualization tool that I did right down here, right? If you had stresses that were acting like this, oop, didn't mean to do that, okay? Stresses that act like this, that would have the effect of making an element turn into a diamond in that direction, right? And that means that if you were to rotate your coordinate axes such that they aligned better with that new axis where that diamond effect, shape effect is happening, then you're going to start seeing more higher normal stress in that direction, right? Because there's more strain in that direction. Okay? So this, hopefully that helps a little bit. Let's actually do one real quick, and I'll just set up a random second, problem that we won't work the whole thing. What if I gave you a problem where you had normal stresses that acted like this? So I have, let's say, I'll say this is a 20 MPa, and let's say I've got a compressive stress here of 6 MPa, and then I've got let's do it, actually, I'll go negative on this one. Okay. There we go. And let's say that is, 7 MPa. Okay. What direction would I have to rotate my coordinate axes? Let's say this was x and this is y. What direction would I have to rotate my coordinate axes to find my highest principal stress? Okay, so I hear someone say, would it have to be clockwise? So you're saying that I should have a y prime axis that was like over here somewhere and an x prime that's over here somewhere? Okay, is that the direction that the shearing stress is stretching this member? Okay, so I started out with a high, my highest normal component, right, in a tensile direction was this 20 MPa, but it looks to me like the 7 MPa shearing stress would actually start to make this thing elongate more like in this direction, right? Something like that. Well, doesn't that mean that we should have to rotate the coordinate system counterclockwise to find where that highest principal stress would be? Because it would have been aligned with the y, but now we want to rotate that y counterclockwise a little bit to catch where that maximum principal stress is going to be. Okay? Here, I'll tell you what, I'll sketch, it'll take me like just a second here to sketch what the Mohr circle diagram would look like. How would I do that? Okay? I would have a 20 MPa that would be over here somewhere. I won't try to do this one perfectly to scale. I would have a 6 MPa that'd be where? Over here somewhere. Okay. Where I had my 20 MPa, do I have a positive or negative shear? Negative because why? Because it's going to try to rotate this square counterclockwise, right? And so that would be down here somewhere, maybe like right here, and then up by the same amount over here. Do you agree with that? So that represents the state of stress that I'm actually given. And then what? In order to find my principal stresses, I would have to rotate counterclockwise a little bit to figure out where my principal stress values were. Okay? And keep in mind, this over here represents that 20 MPa, and this over here represented the 6 MPa. Okay? So basically what I'm saying is, if you think about this rationally and think about what direction the shearing stress would skew the element, right? That gives you a clue as to the direction you would have to go rotationally to get to the coordinate axis where you would have a principal stress. Okay? Maybe that's given you at least something to think about.